Hi folks, it's Jeff here, Victor Echo 1 Zulu Alpha Charlie, in the southwest side of Nova Scotia. And I'm going to give a little presentation here on how I turned two of my backyard 160 antennas into a usable array. It's a bit of a long-winded experiment and project I've been working on for a year or two, and I've got some results. So I wanted to explain what I did and how well it worked out. So you have to bear with me. I'm not the most competent mouse slide operator here, so I have some PowerPoint slides I'm going to speak to. Some of the slides have a little caution on there. We're going to talk about complex impedance and modeling and some experimental antenna things that some people don't really want to hear about. So if you're one of those people, I really recommend don't be disappointed. Go off and do something else. But if you're interested in how my experiment has worked out and you like experimenting with antennas and you're somewhat interested in what you can do with understanding a bit more about how antennas work, carry on. You may find this entertaining. You may know more about it than I do, in which case I'd like to hear from you. So this little labels on some of the slides. There's a little apple here when it says, be careful. You might learn something here, so view at your own risk. So this is my place with a Google Earth shot. I'm on the edge of a lake, and these are the two antennas. So one is an 80-meter OCF off-center fed dipole. It's up about 70 feet. And the other one is a classic 160-meter L antenna. It's also up about 70 feet. And they're kind of roughly in this position. The bases are 167 feet apart. I have two because I really, in my location here, in the kind of 160 work I do, I really like to favor the southwest or sometimes favor the northeast. So that's why I have these two antennas. And they do that. Your classic L is a little bit leany towards the non-pointy end. Not by much, but maybe 1.5 dBs. And the OCF kind of works that way. It's like a flat top T antenna, but it does tend to lean a bit more this way to the southwest. And I have some other antennas spaced around the property too, but these are the two we're going to talk about. So I have these two normal antennas, and both have some random radials. And the goals are to see if I can make a useful array. I do want to use full power, and I would like to have the effective radiated power gains to the northeast and southwest to aid contesting. And we're going to look at, if you think you've got something, how do you figure it out, whether you do or not. So a little bit of do-it-yourself antenna ranging. And I need to move this window here a little bit. There we go. And on hand, I've got some typical antenna analyzers for measuring impedance. I'm a long-time user of VE1ZAC modeler, and I have the basic NEC2 calculating engine in it, the one that comes with it. But I also have a license to operate NEC5, and I'll address that a little bit. Excuse me. You don't really need NEC5, but since I have it, I'm using it. I'll talk a little bit about that. I've also got lots of tools and wire and big junk box and good trees, and I got apps for helping design L matching coils and circuits. Got a good coffee pot. I've got a helper dog, the usual. So how do we deal with creative antennas? Well, I have to apologize for this, but I think it's absolutely mandatory that you know how to make measurements on your antenna, especially at the base of the antenna. But if you can figure out how to move your base antenna's calculated impedance indoors at the end of your transmission line, that's also handy too. So you need to know how to do that. If you don't know how to do that, well, I'm not going to explain it here, but it's mandatory. You need to know what this R plus or minus JX is, and you need to keep track of that for parts of antenna projects. Now, I'm also going to say it's almost, not completely, but it's almost mandatory to acquire some modeling skills if you're going to do this kind of thing. You don't have to. If you sort of have some idea of what you're doing, you can just build it and see how it works. But I can tell you, it's a hell of a lot easier to use modeling. And this is not as hard thing to learn as it used to be. There's so many YouTube videos about how to use it, and people like me are always willing to spend some time helping you with modeling. I've been at this since VE1ZAC first came out, so like over 30 years. And I'm not a power user, but I'm a handy user. It's also really useful if you want to pass your results around to other people, because everybody else who experiments with antennas tends to do the same thing. So here's a few modeling notes. If you want to get creative with antennas, it's really hard to avoid doing modeling. And I would just give you this. If every hour you spend fooling around with modeling is going to save you multiple days of building and screwing around with stuff outside. So the ratio of, like, the advantage is huge. Good modelers are basically free. The two really popular ones are VE1ZAC and NEC Win 4, whatever it's called, WinNEC 4. Those are both pretty much the ones everybody uses. VE1ZAC used to have to pay a little license fee. It was created by Roy Llewellyn, a longtime RF wizard. He worked at Tektronix forever. He's retired now. And when he retired, he didn't really want to keep supporting VE1ZAC versions and everything, so his idea was take the pro version and make it free. Very nice of him to do that. So you can download it and operate it in its pro version for nothing. Just do it. It only runs on Windows. Some people have ported it to Linux through Wine. I'm not sure if that works or not. I've never tried it. It comes with a US government released old-time electromagnetic calculating engine called NEC 2. It works very well. VE1ZAC includes some patches to make it work really well for amateurs. NEC 5 is the latest released commercial version dealing with wires in and near the ground. The original one, NEC 2, is not as good at that, although it still gives you very good results. But the advantage of NEC 5 for amateurs is that it helps sort out issues with wires on or in or near the ground. You can get NEC 5, or how you get it, at least how I got mine, is you have to go through a little bit of a security sweep, basically answer a lot of questions, provide an affidavit, a non-disclosure agreement. You're only allowed to use it in your home on one computer, and you can't take it anywhere. It seems a bit weird. There is a license fee. So I find it, if you do use it, I believe that you could probably increase the accuracy of your models by maybe plus or minus 1 dB. So you could live without this. But if you're looking for absolute numbers, it may help you out. But I don't think I would approach this and say you have to have NEC 5. However, the results I'm going to show you were done with NEC 5. And like all good things in hand radio, you want some good results, you got to go the distance. You got to put something into it. So the characteristics of my 2Ls. One is a classic, what they used to be called a Wyndham, but it's really not. It's an OCF dipole. Mine has been modified a lot and I use it. It's my favorite antenna. I use it a lot. So it's the junction point, the off-center fed point, has nothing up there, just a connection of 300 ohm twin lead ladder line, the good stuff. And at the bottom, there's a kind of a network which can allow it to work as a classic OCF dipole, or you can switch it to becoming a Marconi antenna. So you join the conductors together and work it against the ground. And there's L match and switching stuff at the bottom. I'm not going to go into that. If anybody's interested in that stuff, I'll send you, I'll do another little video, or I'll send you some drawings of what's there. But suffice it to say, there's an L match which provides a 50 ohm feed to coax at the base. And I find that it tends to favor the southwest with the way I have it set up before I started this project, with about 2 dB at 35-degree takeoff angle, maybe 25. The field L, the one over away in the other side of me in the field there, is it's also dedicated to 160 meter. It works against radials and tends to favor the northeast by about 2 dB. I've converted both of these to single tune radials. I'll explain why here in a minute. This is how it works. So phase one of this project, I got 3 phases. So phase one is the single directional tune radial discovery I made. Phase two is how I accidentally discovered that I made a passive array and didn't realize it. It was a modeling accident. And then phase three is how I turned it into a phase control array. And then there is a sort of a phase four, and basically improving radials. So phase one, the single tune array. So one day I was trying to figure out how I could improve both these radials in their favored directions. Could I make them do a little better? And I discovered by playing with radials in the model that if you use a single tuned array, tuned radial, pointed in the direction you wanted to go, you could increase their ERP in that direction. So basically you can add about a dB. So I found that a radial type L is about 1.5 dBi around one way compared to the other. But with the single tune radial, you could increase that to about 2.5 to 3.5 dBi, depending on a few things. The length that I chose my length via modeling trials. You could also do it by just adjusting it. You know, just keep hacking the thing or folding it up and seeing how well it worked. But I kind of optimized it by modeling, and I put my radials out that way. So with the L leaning to the southwest and one leaning to the northeast, its effect is seen as almost 2 S units. It's quite surprising when you switch between the two. Not quite 2 S units, but almost. How do I know that? Well, that's what I calculated it would be, but I confirmed it with a ground wave QSO to the northeast and reversing, going back and forth, so that was very helpful, with another ham. And I also did a whole lot of RBN testing, which is just the greatest tool for this kind of thing in the world. And I really appreciate what RBN does for you. And I even made a contribution to RBN because I was so thankful for its existence. And then I also did quite a bit of testing in Stu Perry contests and the International 160 contests. And the performance agreed with what I measured. So antenna ranging, well, reverse beacon network, of course, is a big thing. Can't recommend that enough. But I also kind of set up an ad hoc drive around ranging system. And what I did was I picked a bunch of sites located about 1 to 3 kilometers around my location. And I built a little clip-on window antenna that went on my car. Excuse me. And I set the transmitter to transmit about 5 to 10 watts as a carrier, and then moved the receiver around each of the sites and took a reading. I used an SDR, in this case an RF Space SDR1, and a notebook computer running HDSDR software. So it's like having a little portable spectrum analyzer you took around with you. So I collected the comparison readings with that, and then of course you get data on where you are and how far you are from your transmitter on Google Earth, another great tool. So you put all that junk together in a spreadsheet, you do magical statistical junk, and you wind up normalizing the readings for range and plot, and you get numbers. Then I also did some on-the-air ground wave tests that are a bit more anecdotal, you know, with friends, other hams, and then I operated contests. Stu Perry especially is very useful. So this is my do-it-yourself range location. This is where I live here on VE1ZAC Lake. So these are all sites that I could repeatedly drive to 2 or 3 times and make measurements. And they're located all around me 360 degrees, so I got some range and bearing information to each one. So that allows you to normalize the reading you get for distance using the inverse square law. And plus you get bearing data. So it allows you to make a plot, basically, to see how well you're doing. That worked really well. So that's what I had before I started playing with improving it. And during the improving, I ran across a discovery. I never at any time put both antennas in the same model. I just had them as separate models. So one day I said, gee, I wonder how these things might work as an array, and I stuck them in the same frame in the modeling. And lo and behold, I discovered that I actually had a passive array arrangement without me knowing it. In other words, they interact with each other. So the model said, Jeffrey, you have 3.6 to 4.2 dBi forward gain, and between 1.5 and 2 S units, which is like 10 to 12 dB front to back ratio at around 35 degrees elevation. And this is using the directive single tune radials that I had already set up. So I confirmed that it was true. So I was over excited about my single antenna results, not realizing that I actually had some array performance. In other words, it was better than I thought it was, according to the modeler. And it confirmed that my observations kind of said, yeah, I'd seen better results than what I had predicted. So this showed the results were more in line with passive array. So the takeaway lesson here is you really should look at all the potential close by elements the first time. This was a surprise, a nice surprise, but I felt a little stupid that I had done that. Some people might ask me, yeah, I use NEC 5. I repeated the mini NEC ground model through all of my tests. The radials are shown as slightly elevated off ground because they're not buried in ground. They're sitting on grass and field weeds and stuff. So they're up about, I showed them as being off the ground by 6 inches. The truth is, some are, some aren't. But I do, for maintenance, once a year, I go and lift all my radials up, let them set back on the ground. So in the course of a year, they will settle down, with grass growing all over them and stuff. But I always do maintenance by pulling them up once a year. I also measured my ground one day. I made a little ground probe, made measurements with an antenna analyzer, and plugged into a online calculator by some German hams and actually came up with conductivity numbers for my ground. And I select the ground characteristics matching that when I use VE1ZAC. Okay, so that's my second phase. So we're done with that. It worked really well. Phase 3, I wanted to get into trying a phase controlled array. This is more of the classic, you know, you have 2 feed lines and you phase control your transmitter between the 2 of them. So the pros of doing that with my 2 antennas are that they were 167 feet apart, and I had 2 transmission lines that came into the shack. And both antennas have matching devices at their base, which allows them to have pretty good low SWR connection to 50 ohm coax. The cons are that the feed lines aren't the same and the elements are not the same. So that's why modeling is so helpful to you, because it takes into account a lot of that stuff. So modeling the existing single tune radial showed possible 4 dBi forward power and 10 dB optimized in around 120 degree phase shift feeds. And that corresponded with my observed performance. But modeling with, I improved the radials, and, well, one antenna I just plugged all the radials back in, the other one I added radials. And basically I looked at how it looked with 90 degrees as well, and I'll explain why I did that. Which is typically what you see with more array performance, but only because people try to build arrays around certain things. So when I did that, I could see that I could just about reach 5 dBi, decibels compared to an isotropic antenna, as forward power, which is much better than 1.5, which is what you get from a single antenna. And in some cases, I got up to 22 dB front to back ratio, which is pretty impressive. So how to accomplish this? How could I go about doing this? Well, excuse me, this is a little diagram of what I have. So this guy on the left is my OCF antenna. I guess I'm showing it about 75 feet high. That element's replaced now with a 300 ohm twin lead as an element. It doesn't really make much difference since it's really used as a Marconi antenna here. There's a matching device in the base, and I have a 71 feet of coax that comes into my shack. Then I have on the field L, I've got basically the same kind of thing and a match, and I've got 190 feet of coax that comes into the shack. So I've got these 2 ends that come right into my shack, so I can deal with this thing inside. I don't have to do much outside. That's gave me some encouragement. So to phase control the antennas, the first thing you need to do is realize that you need 2 feeds that you've got in your hands inside that need to see, basically, the best world is the elements are the same and the feed lines are the same. Well, I don't have them the same. But what I still need to do is have identical feed lines. And what I mean by identical, they need to show the same delay and the same impedance at each end. So to do that, I had one nice long one that came in, and I had the other one that was short. And I was playing with two different ways to do phase control of the array. So one is the Chrisman method. I'm not going to get into it here. You know, I'm a great fan of the Chrisman method. I've used it for a highly successful way to do antenna array stuff. It's technical. It's hard to figure out. You need to be a little bit of a wizard with spreadsheets, and you need to be good at using, doing antenna measurements with an analyzer. And it's hard to start this without good array data. You kind of need modeling data from an array before you can start into it. However, if you can do all that, it's an excellent way to build arrays, especially if you want to not use 90 degrees, if you want to use something like 120 degrees, whatever. Chrisman doesn't care. You can tell it what you want, and you can figure out the right lengths. Plus, it's all just coax. I wrote that off because I couldn't see that happening, and the lengths I had to deal with were pretty long, so I skipped it and decided to go right to a quadrature type hybrid phase delay system. So what that one depends completely on going 0 to 90 degree phase shift between the two antennas. So I said, fine, I'll start with 90 degrees. It also showed the best front to back ratio as compared to trying to do it with 120 degrees. You got better forward gain, slightly, maybe half a dB better with 120 degrees, but you really lost in the front to back ratio. When you use the 90 degree system, you lost a little bit of forward gain, but you did really much better in front to back. And front to back's important, especially for us here in the Northeast, or in the East Coast, North America. So the ideal is to have quarter wave delay lines, which can be emulated, but with a hybrid quadrature system, it's kind of built into it. So my real job was to get the transmission lines fixed up. So how do you do that? Well, this little summary sheet explains a little bit about how you do this. So the quadrature device is basically a transformer you build. In this case, it's a pair of, I used a pair of T200-2 toroids, powdered iron toroids, and I glued them together, and that, I reckon, made me a big enough core for use with an amplifier with power. And after you build this thing, you wind up with 4 ports on it. That's what the quadrature is all about. So you put a feed into the thing. When you put a feed in, you get 2 things out. You get a 0 degree output, and you get a minus 90 degree phase shifted output. You also get another output, which, if things are balanced, if you have nice equal loads on these two, you get nothing out of the 4th port. But if these aren't balanced, and things are going a little wonky on you, this radiates power. So what you do is you put a dummy load on this and a watt meter, and it gives you a little health monitor. So the idea is, if everything's working good, you don't see anything on the watt meter, or very low, But if things are going wrong, this will start creeping up. And if you're getting over 15 or 20 watts out of here, you've got problems. So it's a great little feedback indicator of how well this works. I really like that. And since this thing is inside with me at the shack, my watt meter and dummy load was sitting right there. I can see it. I'm a great fan of this quadrature thing. By the way, it's the first quadrature system I've ever built myself, and I'm quite pleased with it. Now, looking at the 2 feed lines, one of them was 71 feet, and I measured the impedance in the shack, so it was okay, but it turns out that I've got something like half a wavelength here, which is not good news. What I really wanted to have was not have wavelength. You want to kind of get quarter wavelength or 3/4 wavelength or something like that. So what you got to do is modify this in order to get to something which you can repeat with the field L. So my field L already had the 0.55 wavelengths long. That's what 194 feet is, or whatever, coax. And there was the impedance. So I had to do a little correction to that as well. And I did that by basically building some little LCs to plug onto these things. Now, to get my Marconi feed line delay to be the same. I found this didn't work well trying to use an LC. I could make it match, but I couldn't get the right delay, and it seemed more complicated than it was worth, so I just said, hell with it. And I just bolted on a piece of coax onto this, so that basically I had two similar lengths of coax in the shack, and this length of coax is just coiled up on the floor underneath the quadrature box. That worked fine. So I made this little sheet to keep track of these things, because you do them all as individual little projects. Anyways, that all worked fine. There's my little quadrature transformer. There's a little picture of it there. So it's like, say, it's two T200 cores with some big fat wire for the turns. Each of the turns is 4.3 microhenries. That's important for 160 meters. And I've got it mounted on Teflon block here holder. I don't go out and buy Teflon for something like this. I just happen to have some pieces, so use what you got. And I kind of built my thing dead bug style. So I have some interesting piece of copper material, board material, that was not your normal G10 type stuff. It was more like plexiglass. I don't know, this was surplus stuff I found. So I made a frame and a connection place to make this whole thing on out of this, and it worked really well. So that's my transformer, my hybrid transformer. And this is a little conglomeration of pictures. This is the quadrature device. So you can see the adapter coils. These are LC gadgets that have a coil and a little capacitor on them to make this work right. And you can measure this stuff individually with your inductance analyzer, and you can measure the phase delay, all that stuff. So I wound up throwing away the one that I was using on the OCF dipole. That's this one. So I don't use it in my final version. This is the final version, so you can see I took it out. And instead, I have just the right length of coax to make this work. And that's how I got both of the delays in the thing to work right. To switch this thing between being inline and being forward and reverse, I found on Amazon these great little antenna switching boards, which are cheap, with relays on them, and I don't know, they're like 40 bucks, 50 bucks. Great way to make switching stuff for your antennas. And I used one of those and just modified the traces a little bit, cutting the traces a little bit, so I wound up with a little relay system I could live with. And that was quick and dirty, and it worked really well. So here's the thing, not in a box. It is now in a box that it lives in, but I just have it sitting on a chair there. And here you can see a 100 ohm bird dummy load and a 43 type 43 watt meter that when I'm operating this, I set this up on the operating table so I can see it. So the idea being you can quickly see whether your array is working right. And if you start seeing power creeping up in this, you need to go back and figure out what's wrong. In my case, I have a way to adjust the match on both my antennas, so I can go offline, adjust them, and get back online. So that's the build. We won't go into details. Now let's look at the results. So these are EZNet predicted results. Not exactly what I wanted. This is kind of how my two antennas are spaced apart. And this is north. So really it would be nice if I had this thing rotated so this notch was more up here. But it's not bad. So this is one way. The profile, if you look at the elevation, I'm really pleased with this. It's effectively working really well at about 25 degrees. So between 20 and 35 degrees. So really good for DX work. You know, it's quite good. I'm really pleased with this. It's not any good for straight up and down stuff, of course, but the 160 is not really a great straight up and down band. It's either first hop or ground wave. So that's one way, and here's the next way when I turn it around and feed the other antenna, or basically reverse the thing. Same thing. It would be nice if I had this notch down here, but you'll see that it actually produced some pretty decent results for me. And I can confirm these two readings, if you like, these predicted readings are kind of about what I have, very close. So here's a little chart. So what I wanted was to see how it performed in the northeast. So with the OCF, with the notch at the OCF end and the forward gain, the field LN, I got about 4.9 dBi to the northeast. And when I reversed it, I had about 3.6 dBi to the southwest. So definitely I can do better to the northeast than I can to the southwest. And surprisingly, that's proven out to be about the way it works. What I did find is that because my antennas are not kind of spaced correctly for the right direction I want to go, I did find that the best performance to the west was due west. Yeah, I could live with that. You know, I get my 4.5 dBi to the west. I'm okay with that. Surprisingly, both ways have a bit of a north component that doesn't go away, but the south component changes a bit. So I kind of plotted all those, and I can confirm a lot of that. It's pretty close to being the right thing after looking at RBN testing and contest results over about 6 months. And just if you look at the deltas between the two, if you look at switching your switch between forward and reverse, you've got about 7 dB to the northeast. You've got about 11 dB to the southwest. East, huge notch. You've got about 24 dB, and west, you've got about 10 dB. In north, like I say, it's kind of up there all the time. It doesn't really change. And south kind of is more change, but not as much. So that's the results I got from doing this. Am I happy with this? Yes. It's okay. Now, an observer might say, gee, Jeff, what happens if you feed both elements at the same time? I don't do that, and I haven't done it yet. This is untested. But I said, well, let's see what it looks like. Surprisingly, it's got the right directions going for me. This is the northeast here. This is, you know, about northeast, southwest this way. Well, this thing kind of favors that. Now, the lobes aren't very deep, maybe 3.3 dBi, which is, again, about a 1.5 dB better than a single L. So you do have some advantage. Without doing any switching, you're going to favor southwest, northeast, and northwest and southeast would be the worst. So you've got like an S unit difference between them. So if you just wanted to run a single antenna in contest and you didn't want to do any switching, hey, this would be all right. I don't mind throwing a switch around, switch stuff. But if for some reason I didn't want to do that, this would be a good way to go. I would have to adjust the matches to drive the two of them, but I'm not really interested in doing this, but it would be very easy to do. So there you go. So there's the whole result. So my takeaway from this is worked really well. I'm really pleased with the results. So without setting out to build, you know, proper, big, long, high towered type array, my two L's turned into a pretty decent array, and I can say they do work for me. I definitely got better results than I have with a single antenna. So that's the takeaway. So I hope you all enjoy this and have fun with your antennas. I hope to see you on 160. Cheerio. No.